won't have a problem with this. Now, keep in mind, these are people who build analytical instrumentation for a living, and they don't have a problem with it. I said, okay. So, anyway, by the time we got our partners involved and got the stuff produced and got it back to them, they had sold their fuel cell division to United Technologies. And United Technologies had had the people come work for them for a few months, and then the people actually quit United Technologies and went and started their own study group called Giner Incorporated in Waltham, Massachusetts. And so Tony LeConte went with them to the head of their fuel cell division at Giner Incorporated. And so by the time I get back with my material, they're at Giner Incorporated. So I said, well, great. Now you can sign a confidentiality agreement where you won't talk to anyone about this, and we'll work with you. So we paid them to do the fuel cell studies. As received, the rhodium we sent them, the alleged rhodium is what they referred to it, or the rhodium substitute, didn't have any rhodium in it. They sent it for analysis, no rhodium in there. Then they mounted it on carbon, and when they do that, it goes black. And they put it into fuel cells, and they tested the fuel cells for about 3 weeks. And then after they did the 3 weeks of testing, they tore down their fuel cell and sent the electrode back for analysis. And now it analyzes to have 6 to 8% rhodium on it. The rhodium had mysteriously appeared from no place. Well, needless to say, they were very impressed, because rhodium sells for a lot more than platinum. Rhodium is quite valuable. It's a lot more valuable than gold. And here we were getting it from no place. It was mysteriously appearing. So they said, Dave, it's our opinion that nobody understands this. Big revelation here, you know. And I said, yeah. And they said, well, Dave, if you're the first one to discover it, if you're the first one to explain how to make it, then you can get a patent on this. And I said, no, I'm not interested in patenting this. I'm not interested in that. And they said, well, come talk to our patent attorney in Washington, D.C. So I went down to Washington, D.C., and I figured, well, I'll just give him an hour or two to talk to me. And one of the things this patent attorney told me, he said, Dave, if you don't tell anybody about this in a patent, if you elect to keep it proprietary and secret, then if somebody else discovers it and they file for a patent on it, they actually can stop you from working with it. Now that didn't sound right. But he says, that's the law. So I said, well, gee, maybe I do want a patent after all. So in 1987, we filed U.S. and worldwide patents on orbitally rearranged monoatomic elements, or what we call ORMES for short. That was a name that we just were flying on an airplane trying to come up with a name, and I said, this guy was with me, he said, how about this? And I said, no. And he said, how about this? And he said, ORMES. And I said, yeah, that sounds good. Orbitally rearranged monatomic elements, ORMES. So we had ORM gold, ORM platinum, ORM palladium, ORM silver, ORM rhodium, ORM iridium, ORM ruthenium, ORM osmium. Anyway, we filed those patents in 1987, and the patent office really objected to this. They said, Dave, in your patent, you're not being specific enough about the weight of this material. And I said, well, the weight isn't constant. If you produce this stuff as the pure gray-white powder and you take it out of the tube furnace where it hits the air, it says wait for 2.5 minutes, then weigh it, and you wait 2.5 minutes and it's still gaining weight. You wait for 5 minutes, it's still gaining weight. The scales are continuing to increase, and you wait for 15 minutes, it's still gaining weight. And I said, where do you report the weight? What's the real weight of this stuff? And at what point you say, okay, this is it. This is the weight. They said, well, we've got to have some precise numbers. You can't have estimates. You can't have approximates. And I said, well, it depends on how long you wait. And they said, well, get something where you don't ever have a variable. And so I said, well, that means we've got to be able to heat it and hydrogen reduce it and then weigh it and never have it get out in the air. And so I asked the PhD chemist, I said, is there any machine that would allow us to do this? And he says, well, yeah, the most specific one you can get is called thermogravimetric analysis. And I said, fine, get one of those machines. He says, well, about $380,000. And I said, on second thought, don't get one of the machines. He says, but Dave, we can lease one for about $6,000 a month. I said, well, good. In 2 or 3 months, we could get all the studies done, and we'll send it back. And he said, okay, we'll bring one in. So this is a machine that's all atmosphere controlled. It's computer operated. It's all atmosphere controlled. It has a microbalance where you actually can put the sample in on the balance, and it weighs the sample while you oxidize it and hydrogen reduce it and anneal it, all while you're weighing it. It never comes out of the atmosphere, the controlled atmosphere. It actually is weighing it in the heating apparatus. I said, well, that's everything we need, right? So we bring this machine into town, we set it up, we start running this machine. So we oxidize it and it goes to 130%. We hydrogen reduce it, it goes to 103%. Now, everything's so far so good. And then we anneal away the hydrogen, it goes to 56%. I said, wait a minute. It was 100% to start with. We went to 130% we oxidized, 103% we hydrogen reduced it, and now it's 56%? Did we volatilize away part of the sample? Did it vaporize due to the high heat? So we took this 50% of this white powder and we put it over on a quartz boat. And we weighed the quartz boat, we weighed the powder, we put it all on the quartz boat, and we heated it up to like 15, 1600 degrees where it actually melted into the glass, the quartz. And when it melts into the glass, it turns black and all the weight comes back. So the mass never really left the sample. It just, when it was in there, you couldn't weigh it. This doesn't make any sense. I mean, this is not possible, right? So I said, well, let's do this again. Now let's oxidize it, let's hydrogen reduce it, and let's anneal it again, and let's turn it white. And sure enough, it went down to 56%. I said, well, let's cool it, and then heat it again, and cool it, and heat it again. Never take it out of this machine. And so when we start weighing it as we're cooling it, the weight goes to 350, 400%, down to 56%, 200% down to 50%. It's jumping all over the place. I said, well, let's heat it again. So we, without ever taking it out of the machine, we start heating again. And it starts going less, and it goes like 20% of the weight. And then it'll collapse back to 56%. So then we cool it down again. This time it goes 350, 400, 500%, and then collapse down to 56%, go up to huge amounts and collapse down. And this is like over an hour and a half to 2 hours time. It's floating. And I said, well, let's heat it again. So then we just heat the same sample again, and this is all under a total inert gas, and it literally goes to the point it weighs less than the pan weighs it's sitting in. In other words, if the powder wasn't in the pan would weigh 0. With the stuff in the pan, it weighs less than 0. And yet when you cool it back down, there the stuff is. It's never left. It's still 56% of the correct weight. But every time we heat it, it would go less than 0. And you know, when you look in there and look in the pan, it's not there. It's gone. The pan's empty. And yet when you cool it back down, it begins to form around the outside, and you see it solidify, and there it is again. We had no explanation for it, people. I mean, we were totally dumbfounded. So I went to the manufacturer of the machine, and they by the way, they did give us magnetic standards that came with this machine. You can actually take a little salt crystal and put it in the machine, and you heat it, and at 250, 300 degrees, it would become magnetic. And then at like 650 or 700 degrees, it would lose the magnetism and go to a normal material. Then when you cool it back down at 650, it would become magnetic. 350, it would lose the magnetism. And it was actually a standard that you put in your machine to check it, see if it was, interacting with the magnetic material. When we put the magnetic material in and heat it and cool it, nothing happened. It weighed just perfectly. So it wasn't an interaction of the field of the heating machine with the sample. And yet we put this stuff in it, it didn't make any sense at all. I mean, it was crazy. It just, any weight you wanted, it seemed to be able to be weighed that way. So I go off down to Verian over in the Bay Area in California, who makes the machine, the Verian Corporation. I said, look at this data here. It makes no sense at all. What's going on here with this machine? It's got to be something you can explain, right?